So good morning, everybody. Again, I think it's time to come back from the break. So to begin with, I have two questions for you. First is, can you hear me well?
Yep.
Yeah, thank you. And the second is, can you see my screen?
Yes.
Yeah.
So from the last lecture, we have uploaded 3 exercises in Canvas, so you could find it here, then here. Today I will cover the last 2. I will skip the convolution exercise because it's kind of just coding. But in the later exercise, we will use the code that could be written in the first exercise as it is given. I would like to structure the seminar like live coding session, so I will implement the solution step by step, and sometimes asking you to suggest or to guess the particular part of solutions. And after the seminar, I will upload the solution notebooks to Canvas as well, along with the exercises for the next lecture. I would like to start with the last exercise, lump detection. I think it is the most interesting one among them, and it is the most useful to say for the first homework. So just to look into the first assignment. The goal of the first assignment is to count the trains, and then having the trains counted to calculate the total score according to the length of the roads. And to calculate the scores, you need to separate the train roads between themselves. So you need to detect the cities. And as you can see in the, in the specification, you need to return 3 things. The first is centers, and the last 2 ones is the number of trains and the scores. So the centers are the one thing, and the first you need to obtain from the image. And the template matching is the most useful algorithm to detect the city centers. And as you can see, the city centers are quite close to in the terms of shape, for example, to lamps. So I will start with the imports and useful functions that were also given to you in the exercise notebook. So they just import some libs useful for the solution, and gives you some utility functions to plot the image. So first step, then they are going to detect lamps, is the template matching. And for the template matching, they need basically 3 things. The first is the image itself, and we have an image. The second is the function, the convolution function. And here we have actually an implementation of convolution in NumPy, which you were suggested to implement in the first exercise. So they're actually forgiven in the last exercise. And the third thing you need to run the template matching is the template itself. So the kernel with which you could calculate the with which you could convolve your image. So I believe that it will be working from scratch. And let's start with so the first step will be, of course, to obtain the template. So the easiest way to obtain the template is to crop the image by the simple indexing. So to say, I want to take this lamp as a template. You may search for the indexes iteratively, for example, to plot the shape of the image, to crop the large image, and to reduce the crop itself. But I will use so previously obtained by me numbers, and here we could see, I believe, the largest lamp on the image. And let's compare the results of the okay. I will address the question in the chart along with I'm going through the solution, so I will respond to the message of Denise a little bit later. So let's first compare our convolution function with the template matching of scikit image. So our function takes as input two parameters. The first is the image itself. And of course, we will be working with the grayscale images. So I have loaded the original image, and later on I have loaded the image in the grayscale format. So it is the simplest way to use convolution, not to care about other RGB channels. And let us visualize firstly the convolution that we have obtained, and secondly the convolution from scikit image. And you can see a large difference. So basically in the scikit image, you already could see the high values of lamps or the lamp regions, so you can work further with. But in traditional convolution, the results are quite messy. So it is the first question to you: what is the difference between these two methods? Or what is the different in the template matching on the scikit image? And Denise is already providing you with the answer in the chat. the right answer is the normalization of image and of template itself or the kernel. So in the default template matching in the scikit image uses the normalization of image and the kernel. Just to show you how it looks like mathematically, I will also post the link in the notebook. So the normalized correlation or convolution looks like this, normalized cross correlation. So instead of simply multiplying the image or the image region here is the f function and the kernel is t function. You you firstly subtract the mean, and secondly you divide the result by the normalization, by the sum of squares of the standardized image and kernel. By standardized, I mean the subtracted mean. So I believe we might simply implement it into our convolve function by adding some parameter, and here I just want you to showcase how we may modify our convolve function and how it looks like in the Python itself. So assuming we have an input image and an input kernel, if we should perform the normalization operation, the first thing to do is to normalize the kernel. So I will calculate two values. First is I call normed. I subtract the mean value of kernel. And secondly, I recalculate the normalization parameter, the one in the denominator. So it is just sum of normed kernel. And then we are iterating through the image with our kernel, we should modify the convolution operation. So it's again split it into two cases. If it is not normed, then we perform the standard operation. So the first thing, we also need to norm the patch in the similar manner. And so we just need to extract it. And secondly, we should perform the convolution operation. So addressing this formula, we need to take a product of normalized convolution and convolution kernel and image window, or as I called it, page, and then to divide it by the sum of squares. So the first step will be take a product of them and secondly divide by the sum by the production of sums of squares. Need sum here. We already have calculated it. So I believe that should work, and they also add the normed parameter to the convolve same. And pass it to the original function. So let's try to compare the results between themselves and just add the normed parameter, set it true. I believe this code should work fine. We will check it out in half a minute. Then calculates. So as you can see, the results now are pretty similar, and if you use the normalization of kernel and the image or the patch with which you will perform a convolution, it gives you kind of more detailed structure or more detailed result in this case. So going one step further, I would like to also take a template which is quite larger. So I would like to add a 5 pixels from each side. And assuming they have a larger template, I will presuppose that it will work slightly better. And you could guess why. So given the result that in terms of detection, the larger template works slightly better than the smaller template, what could be the reasons? So this kind of question for you. Yeah, one of the possible answer is the robustness of the larger kernel. So imagine if you have even smaller kernel, so it is just like in the middle of this image. So you will catch all the light structures in the image, but as you increase and incorporate a larger knowledge into your template, so here you just assuming that your lamps are separate objects, and not only separate, but separate and well-defined in terms of shape objects. And if we take a template as slightly larger than they have now, the result probably will be slightly more robust. So let's now proceed with with the follow-up algorithm which takes a correlation map. And the next question to you is how should we obtain the object from this correlation map? I have a feeling that I'm working only with Denise. It's like a personal consultation. But okay, let's try his answer. So now I have applied I have thresholded as Denise suggested, but I still, for example, don't know how to proceed further with this map. No maximum separation. Yeah, the first thing to do maybe is to increase our threshold. So it's okay. Let's assume it is 0.6. So now we have pretty accurate, I would say, segmentation uh, of our lamps. And let me just for stability use the correlation from scikit image. I have even reduced the false positive outcome. Okay, we have a segmentation map, but how we should obtain, for example, boxes or a single detection for every lamp? What is the next step? I actually have two different, kind of similar but different in the small way solutions from Denise in chat. The first is the non-maximum separation after I have a map, but as soon as I have a correlation, a binarized image, I guess I could just find the center mass of every object. It could be done in several ways. The first way is to just simply average every connected component, the coordinate of every connected component. The second way is to apply, to say, the mask of this single component to the image, take the correlation map, take the original values of this image and find the maximum value. So in both of these cases, we need to, so I will read a question from chat, sorry. Yes, actually there is a straightforward solution how to create a bounding box of lamp is proposed by Maxim. We can use contours, as Mikhail told during the election, just to create fit a square in the OpenCV. So you might write the option which will proposed by Maxim, but I will show you the solution with the connected components and the center of mass, and the bounding box which I will obtain will be just plotted into the image by the same OpenCV. The easiest way to obtain the connected components is the label function from scikit-image. So this function just takes as you can see, an input image, and okay, there are a bunch of hyperparameters, but it basically returns the unique values for every connected component. So let me just write a function which takes as an input the correlation map and, for example, a threshold, and set it to default value. And let's just use the function label to get the connected components from our correlation map. So first we need the image, and we apply the threshold to the correlation map, which we have passed to our function. And I just used two hyperparameters of the label function. The first is connectivity. So the connectivity 2 means that if you have to say array like this, these two elements are considered as the neighbors if you set the connectivity to, so it will count the length of the road from this one to this one. By default, the connectivity is 1, and it will only count the connected component if it's the strict neighbor of the center element. So we will use the connectivity equals to 2. So the diagonal values will be also counted as the neighbors. And I also want to return the number of the connected components as the separate parameter, just to iterate over it. And what I would like to do is to return the coordinates of the center of mass of every connected component. So the connected component, or the mask for the connected component, could be found by just comparing the return label. So for this image, the return label will be the zeros for the background, then the ones for the first component, the twos for the second component, and then every integer number for the each new component, every new component. So imagine that we have iterating over n connected components, and we want to calculate the center of mass. Firstly, I want to return the coordinates corresponding to the mask. So I obtain the mask, then I simply return the list of coordinates for the mask. And then I would like to average all the coordinates. So apparently I have obtained the center of mass, and I would like to average them only by the first dimension. So it is the list of returned coordinates. So after this operation, I would have two numbers. The first is the x coordinate, the second is y coordinate. And I would just end the iteration over the connected components. So from the first connected component to the last connected component. So now I have an array of these components. And I also would like to return them as int values. So I will round them to the exact coordinate, to the nearest coordinate, and explicitly cast it to the int. So it is our function. We may test it. And at the threshold level of 0.5, it returns us all the 10 centers. The second part will be the plotting of these images, and I do not want to manually write the code for this. I just copy paste it from the solution because it's kind of not interesting. I will just discuss it. So the function which takes the image or the either the original image or the grayscale image, the points which we have obtained by the local centers function, and then the box shape, just the size of the box which we would like to plot. And it iterates over the points and creates a rectangle. It is an OpenCV function. It takes the original image, 2 points. I believe these 2 points are the coordinates of the square, 2 vertex of the square, and the color, and maybe a width of the image. So I have an image from Denise. And I'll try to open it. I believe this was the image Denise posted in the chat. So I believe it is not the lamp detection, but the image from the OpenCV. And the template was the messy face. Yeah, okay, I agree that argmax would the performance of argmax and the mean of coordinates are working pretty the same. So the thing that you should modify in your solution if you want to use the argmax is not the average of the coordinates, but you should apply this mask to your original image, say to correlation. And then to do something like this. So you find the argmaximum of correlation values, and then just return the coordinate which corresponds to the argmaximum. So I believe this is the solution that Denise proposes in the chat. If I'm wrong, you could suggest the exact solution which you have meant. So by now, let me close this windows. Let's obtain our points with our function. And plot them on the image. So I'd like to plot the shape which is equal to the template which I have chosen from the image. And let's just plot it on the original image. So here you are. This is the results of the detection algorithm, and now you may judge its accuracy by the image. So we have missed a few components. And the question to you is how should we increase? How could we increase the true positive rate, or the recall or sensitivity of the algorithm by our algorithm? Actually, the answer to my question is quite simpler than it should be, as I have formulated, because if we want to increase the sensitivity, we just lower our threshold. And of course, we have, maybe we should go even lower. Now we have close to 1 sensitivity, but but the number of false positive detection are quite large. I would like, before we proceed with the further solution, I would like to show you a useful playground, which will help you in the OpenCV journey, because the algorithms in OpenCV and in scikit-image typically works pretty fast, so you can iterate all the different hyperparameters in just a few milliseconds, and the way in which the most suitable way to iterate all of these parameters in some kind of interaction is the IPy widgets. So I post the notebook with the solution that you can find the code for IPy widgets ready to use in your homework, for example. Then you try different templates, different thresholds, or maybe some different threshold for color segmentation. So basically we need to function the int slider and interact, the function which will interact with our final function, and the function which will create the interaction slider. For the sake of saving our time, I just copy paste the code again. I have created the slider which iterates between the 0 and 100. It will be our threshold, and write a small function which takes the threshold and then correlates it and then plot the result of obtained by the threshold. So now the may interact with the follow function. And there is no need to rerun a single cell of notebook, but just to change the parameter and see how the solution depends on one hyperparameter. So now I would like to return to the chat, and you have proposed several answers. The naive solution, maybe we should crop the image there, the lumps. Yeah, it should work, but definitely should work in this case. But imagine we have an image of the same lamps, but which was taken from the other angle or from the other location. So it is not the general solution, but it definitely will work in this case, of course. And the other suggestion was to use other lamps as the templates, I believe, use different templates. And yes, it will also work. And it will work in the more general case. So it will be robust to the location of lamps itself. So for example, in the homework, you may crop different templates across maybe 5 images even, but now we have only one image, and we may crop several templates. For example, template of this lamp, which I have chosen, or the template of the smallest lamp. But I will suggest you a little cheat code which is called rescale. So as soon as I have one template of one lamp, I just can rescale it to different scales. So I will obtain lamps of different sizes. So I will find the largest lamp. So we may just even check that I have chosen the largest lamp. So I would like to increase my threshold to 1 and it means the perfect correlation. And as we can see, the perfect correlation is only for the largest lamp. And having the rescale, I could generate a set of lamps given only one lamp of different sizes. Now I would like to return the combination of images. So I will match template for every generated by rescaling template. So I will correlate the original, not the original, but the grayscale image. Did the rescale. I will rescale our original template. Also path input. So here I would like to iterate over the different shapes of the template and scale them to the original size of the template. So now I have to take the iterator and let's just start with the template, which is 3 times smaller than our template. So the first element of our, say, correlation kernels will be the template, which is 3 times smaller because we start from the shape divided by 3, and then finish with the template which have the similar shape, exactly the same shape with our original template. It have taken some time, quite longer than the original template matching, but because we have to say 20 convolutions made inside our array. And now we have to I have a question from chat which I have missed. It reshapes image to a given size using some interpolation. I do not know what is the default interpolation mode of the rescale. I believe it is linear by default. Actually, I do not care so much about the interpolation mode. It could be linear or just linear interpolation. Of course, my template will suffer from the rescaling, but from the image it looks pretty solid, I would say. So the main parameters of my template, the shape of this structure, and the relative values of intensity will be preserved. So now we have to aggregate the correlation, the different results of template matching. So what are the options to aggregate this array? The first thing that comes to my mind is to, for example, just to sum all the correlation. And for example, we may sum the already binarized correlation maps. So to say, we increase our threshold and now we have this is the binarized correlation map for every template matching result for every template. Yes, thank you. The axis to 0. And of course, we after the sum, we have values more than 1 in our sum. The mean, the consequent threshold. Maybe, so let's just implement the we may try both variants. Here, I would like to so in this case, we just average all the template matching results. And in this case, we summarize the threshold maps and then just clip the results to once. So if one of our maps have been triggered on the high threshold value, then they incorporate the trigger results into our final array. So let's just check the results. Actually, I have already passed a binarized array to the get local centers, so the values are between exactly the 0 and 1, so I have to pass literally every possible value, could pass every possible value between 0 and 1 to binarize this image again. So this is a result of sum, and let's just check out. Focus centers will define all the one class. Yes. Thank you for suggestion in chat. So this is the result of the sum function, and this is the result of the mean. So the interesting question here is why we lose so much templates. So then we try the min function. So basically we have tried a lot of templates, starting from the size of template, which is 3 times smaller than the original template, and up through the original size. So when we average the results of our correlation, for example, we could find this lamp only with the maybe for the last 3 templates which have been scaled. The other templates with the lower resolution will be too small to detect the largest lamp. So when we apply the mean to our result array, we have the value which is even lower than 0.5 for this lamp. But maybe we should try, say, the lower threshold here. And yes, this works pretty similar to the original. Also, we might again compare the results by interacting with them by widgets and try different thresholds for these 2 methods and result with the best one. You could check it out later on by just downloading the notebook after the lecture. So that's it. We have created a simple algorithm to detect almost all lamps. I believe we even detect the left upper lamp twice. And the sum even detected the lamp beyond the column. Impressive. So if you have any questions about the template matching, we may discuss them before we finish with the second exercise of Kani detection. So there is no question. There are no questions. Let's briefly cover the Kani exercise. So again, the goal of the second exercise was to detect the corners or the edges of our image. And the task is slightly more straightforward than and less abstract than it was in the lamp detection exercise. Here you have only brief description of what you need to construct, what pipeline you need to construct. And here we have a step-by-step instruction. And the first step is to create a Gaussian kernel, and I would just okay, no, I would like to ask the chat first. what is the simplest way to create the Gaussian kernel? Create array of distances from the center. I don't think that the distances is equal to Gaussian distribution. So the array of distances will give us the give us basically the distances, not the distribution of Gaussian. Okay, the scalar product, but scalar product of what? Actually, the scalar product is 1/2 of the solution. But we need the objects, the vectors which we would like to calculate product between them. So basically the two-dimensional Gaussian distribution is the product of two one-dimensional Gaussian distributions. So we may obtain two CDFs, or no, I'm sorry, two probability distribution of Gaussian kernel, and just take a scalar product between their values. So let's just create a placeholder linear space between the sigma values which we want to color, but with the size of one element more, and then obtain the probabilistic distribution by calling the cumulative distribution over the linear space which we have created. Basically, the linear space is just the coordinates from, to say, -3 to 3 with one more element. And then we calculate the difference between two neighbors element of the cumulative distribution of Gaussian distribution. Actually, norm is the Gaussian distribution. And two-dimensional kernel is the product, the outer product of two kernels, two one-dimensional kernels. And we also need to norm it. And return. I believe they get the same image. So now we are able to convolve our grayscale image with the Gaussian kernel. If you recall the last lecture, not the last, maybe the lecture 2, Michaela has said you about importance of the smoothing before we find edges, because then they took the gradient, the local gradient of any image element we have very noisy images to begin working with. So we need to suppress the noise by applying the smoothing kernel. So then we provide you the code of Sobel filters. So just to recall again, the Sobel filters are predefined filters which have these values if you plot them in the two-dimensional space. And then we calculate by them the gradient by one axis and by another axis. And by two gradients, we could obtain the angles, or it's not an angles, it's, I believe, the distances. And after the distances, we have to calculate the directions or the angles of the gradient. So we could plot them. The first is the gradient of the original image, and the second is the gradient of the smoothed image. So we might not see, but even for the original image, there will be a lot of noise between the lines. And here there will be less noise, but the gradients will be kind of thick. And to suppress the unnecessary edges, we might apply the non-maximum suppression. So here, I don't know, should I ask this question or not, because you can easily Google up the algorithm for non-maximum suppression, and the core idea here is just an implementation. It is kind of actually boring to implement this function, because if you remember the non-maximum suppression inside the Kenny algorithm, what we need to do is to take the gradient map, check it in the 8 directions. So we have 0 and 180 degrees angle. We have a y direction, we have x direction, and we have 2 diagonal directions. And in each direction, we check the image if it have the gradient change in this direction. If it is, we leave the original value of the image. If it is not the maximum value, we suppress it. So we, out of the lines, we should leave only the maximum gradient to say in each connected component, just by heart. So result will be like this. So for every line, you will suppress all non-maximum values and leave only the thin lines for the maximum values. So I believe the code, okay, the writing code for this exercise is, firstly, we are almost out of time. So I need to copy paste it and just take a brief overview. So the first steps are, okay, just creating a template array where we will post our results. And secondly, I transform my angles, so my gradient angles directions, from cast them from the real numbers to degrees, and check then simply in the cycle, in the Python loop, I will check every direction, and if it is not maximum, so okay, no, if it is a maximum value, I will leave it, and if it is not, the result will be suppressed or set to 0. There are just a lot of code to cope with, and I believe I just provide you with the algorithm itself. And it is also working quite a long time because we have a double loop in the Python, just like in the convolution. The more interesting part is the hysteresis thresholding, and here we have a few minutes to discuss it. So, okay, the goal is having the binary image. So the values of this image is, no, it's not a binary image. It's to say is a grayscale image which have values between 0 and 255, and the values are the gradient values, the absolute gradient values. So as you have remembered, it is the sum of squares of gradient between x gradient and y gradient. So how should we proceed to implement the algorithm of hysteresis thresholding? Any ideas? What is the function for connected components? So here the connected components are defined by the actual connectivity between lines. So for example, if this line is weak and it is not connected to the strong line here, it will be suppressed. And the function for connected components is I hope I answer your question correctly. While I'm waiting for your answers in the chat, I will create a template result array. So, okay, let's do it step by step. for now. Firstly, we need first we need to define the strong and the weak edges of our gradient image. So the strong edges are the coordinates where the image, the gradient values of the image are higher than the maximum value. The weak coordinates, sorry, are actually the coordinates which are smaller than the maximum value, but higher than the minimum value. So we just change the comparison and add another condition. So here they have defined the strong and the weak edges. And let's just fill our results with the result array. Did the first step. So the strong edges we will define as the maximum value of the image, and not simply a Boolean array. Firstly, they need to differ two types of, even three types of our pixels. So it won't be Boolean array. So we need the strong edges, the weak edges, and the zeros. You mean just okay, I think we could is this the solution which we want to propose? Yeah, so actually they have run out of time, so I would like to stop here. Maybe I have to spend 5 more minutes just for participants who are interested in finishing the hysteresis thresholding, but also if you're interested in, you may find the solution in the canvas maybe in 30 minutes or maybe in 1 hour. So and for who's of you who decide to leave, goodbye. Thank you for the participation, and now I'll just finish the algorithm and also take a break. So basically, here they want to calculate the neighbors, and the simplest way to calculate the neighbors is again to use the label function. And here they want to find the connected components of our result array. So the intuition here is then we find every connected components, and if it contains a strong value, then these connected components should survive. And if it contains only weak values, these connected components should, to say, die or be suppressed. So again, the connectivity will be 2. So we would like to connect the diagonal elements, and the sake of completeness, they return the number of connected components. Then we want to iterate over these connected components. I believe the first step is to create label mask. So we ensure we do not call it several times. So the mask is just the current value of connected component, and we check if the maximum value do not present in the current connected component. So in the result, even in the result, we should suppress this. Yes, we should suppress this result because it contains only weak values. And otherwise, we will provide it with the maximum values. And I believe this is the solution. Okay. We have obtained even better result comparing to the pre-given image. So I believe this is the solution for the hysteresis thresholding, and now the only step, which is the only remaining step, is to gather all the steps together. And as you have seen, every of these steps are working one by one. This is not a problem to gather all 4 function here. So here I would like to stop. Thank you all for participation. The solution notebook will be uploaded in the shortest time. So goodbye.